So in this video, we are going to look into the IR's interpreter. And the time level function is this. You are given a translation unit, which is the whole program, and the argument. So you are basically executing the main function that is residing in this translation unit with this argument. And it is going to return the return value, or it is reporting the error in the program. So this interrupt function is doing two things. It is going to construct the semantics internal state, and the state is directed to execute. So let's look at how state looks like in the interpreter. So recall from the program language course that the semantics of a program is written like this. Let's first have a program. It is basically AST, and it is loaded. And when program is loaded, the semantics your state is returned. This is basically initial state of your machine, your program's machine. And this S, the initial state, can transition to other states. For example, it can transition to some S prime, and then to S2 prime and S3 prime and blah blah. And you can think of each step as interpretation. For example, if you have a for loop, then at the beginning of your program, your program counter is here, and in one transition, maybe you can walk into the next line. So before this and after you transition to the next line, your program counter can transition to the next state, and it is going to execute each instruction inside this block, and execution of each instruction is corresponding to the arrow here, and blah blah blah. So you basically walk through your program step by step, and this arrow is meant to be the each step of your program's execution. And when the execution has ended, and you reach, for example, the end of your program, returning from the main function, then it is going to signal the fact that, oh, I'm returning from this program, and the return value should be this v, and blah blah blah. So this is basically the basic structure of program semantics. So then we have to define two things basically. First, what is this load function? How can we construct a state from a program? That is one thing. And the second thing is this transition. How to transit intermediate state into the next state. So these two functions are what we are going to define for the IR. So this is the type of the state basically. So it has a global map that is mapping the global variables into the memory locations, and it has a stack frame that is basically the consisting of program counters and registers and all the execution context you need to know about the execution of the function you're currently executing. So if you are in a function foo, then it is going to store the information about the execution of the function foo. And this list of stack frame is basically storing the the stack frame of or execution context of the previous calls. So if main called foo and it called bar, then the information about the bar is going to the stack frame, and information about this main and foo functions are stored in this stack variable. And this is the memory, and you can think of this IR as the whole program. So you are given the whole program inside your states for lookup purposes. When you're going to call to function goo, for example, then you are going to look up in this translation unit that where is goo, and we look up the function and then adjust the stack frame accordingly. So in order to find such a function definition, we need the IR inside, or the syntax inside the state. So this is basically the function load function that is loading the state from the program, but in a different name. You're going to create a new state given a translation unit and the argument. And it is going to return the state, or it is reporting the error when something went wrong. So it is looking up the function named foo inside the translation unit. Then it is going to create the initial stack frame that is consisting of the main function's name, main function's function definition, and the main function's initial block. So it is consisting of such a things. And it is going to have an empty stack because you have only main function inside this, and you're going to have empty prior calls, and you have a default memory, and you're going to be given the syntax of the program. And the first thing to do is allocating the global variables here. So it is basically looping over the global variables and then allocating memory for each of the declarations. If it is a variable, then it is going to store the value, and if it is a function, then it is just allocating the things, allocating the memory. Okay, so far so good. And after allocating the global memory variables, and as a result, the memory is populated with global variables, then you're going to assign the arguments into the registers. So if you're executing a program with, for example, two arguments, ARGC and ARGB, and these two arguments are turned into registers in the IR, and these two values are given to the written to the register here. So write args is writing values to the block argument, and in particular in this case we are going to write the function arguments into the initial blocks parameters. And you're going to allocate local variables. Recall that in IR we have allocations here, right? Each function definition has a list of local variable allocations, for example, for A and B here. And it is allocating the variables, local variables in the memory. So it is similar to alloc global variables. It is looping over the variables and then allocate the memory. So you're given the block ID of the memory. So you can think of it just as a semantic value of the pointer. And this pointer value is constructed, and it is going to be written in the register. here. This RID is going to be the name of the register that holds the pointer to the just allocated local variable, and it is going to be given a canonical name like this here. So this name is just for debugging purposes, and the meaning of this local variable is inside here, ID. So I'm allocating the local variable register of ID. So this is the index inside the allocations list, and for example, it is going to be local name 0. This is going to be the first local variable register, and this is going to be the register that holds the pointer to the index 1 local variable memory allocation, and blah blah blah. So again, similar to the result of the instruction, the result of the local variable declaration is pointers, and they are written to the registers that are canonically named like this. Okay, so after allocating the local variables, then we are done. We are prepared to start execution from the just constructed state. So we're going to return this state, and that is pretty much the everything about what is called load in this figure. We're going to load the program and getting the initial state. So here's that. You're getting the initial state from your program and argument. Then you're going to just execute it. Then how it is looking like? It is basically looping over again and again by executing this step function that is executing one step in the instruction. So recall that we need to define this step function here. So it is just running the step function until you reach the return value. And the main technical meat of this is a step. So in step function, we are going to look up the block that is currently executed, that where your program counter is pointing to. And you first look at the block, and then you see if you have an instruction inside it. I mean, if your program counter is, for example, A's third instruction, then you are going to look up the instruction, and if you have it, just interpret the instruction. And you are not going to return because you just executed the instruction, so you return just none. And if there is no instruction, then it means that you finished executing your instructions, and you are going to execute block exit. So you are going to interpret the block exit, and if it has a return value, then you're going to have it. Otherwise, you're going to just return none. And having return value means that your function is over. You need to return to the caller of your function. And then you're going to restore the previous stack frame, and then write the return value to the register, basically. Okay, so far so good. And if you no longer have a stack frame, then your program is done. Not only your function, but your entire program is done execution. Then in that case, you're going to signify the fact that I'm returning from the program with the return value this. So you're going to do this, and blah blah blah. So again, we split the execution, a one-step execution of a program into two things: the interpretation of the instructions and the interpretation of the block exit. So let's look into a little bit more. So the binary operation, for example, is executed like this. You first calculate the meaning of this operand, LHS and RHS, and get the value. So this is now value instead of just a register name or a constant. So it is a value. And you're going to execute the binary operation. You can think of it as a helper function that actually calculates the binary operation. Similarly, you have a unary operations interpretation like this. And when you store a value, you first calculate the pointer and value, and you basically look into the internal value of internal representation of this pointer, and you are going to store this value to this internal position inside the memory. And then you're going to return void because store doesn't have any meaningful return value. Similarly, you are going to in load, you're going to find the pointer value and then load from the memory. And when you're calling a function, then you're going to get the value of the function pointer value of this callee. And if it is not a function pointer, then you're going to just bail out, and you're going to get the function, and you're going to calculate the argument for the next function callee, and create a stack frame and insert the stack frame to the state. And similar to the program initialization, you're going to write the values arguments into the callee's initial blocks arguments parameters, and then you're going to allocate local variables, and you're done. Blah blah. So that is basically the procedure for a function call, and overall you're just preparing for the next stack frame and then go on. So that's just everything. And yeah, that's done, almost done. At the end of the instruction, interpretation of this instruction, you are going to write the result to this register. This is the temporary register at this block ID with this instruction index. So if you just executed a third instruction, then this register should be A:3. So you are going to write the result of the instruction into this register. So that is basically the meaning of these two lines. And then you're going to increment your program counter so that you can execute the next instruction in the next iteration. So that's pretty much. And yeah, so that is the thing. And yeah. Okay. Okay, so and let's turn to the interpretation of a block exit. If it is a jump or conditional jump, then you're going to resolve the value of the condition depending on which you are going to jump to this then or else branch. Then you just interpret the jump. Switch is almost the same. You resolve where you should jump, and then jump there. And all these three are depending on this interp jump function that is actually jumping to the next block. You first determine which block you're going to jump to, and assert that the arguments of the jump and the parameters of the jump are matching with each other. They have the same length and they have the compatible data types. So you cannot assign integer to float, for example. You can assign only into an integer. And if the type is met, then you're going to actually write to the register. So you first calculate the arguments and then write it down to the register with ID this. That is basically meaning that the canonical name of register again for block arguments. This is the block of the ID of the block ID, and this is the index of the parameter. So you're going to write the value argument into this parameter that is consisting of a block ID and the index of the argument. Okay, so far so good. And you're going to set up the program counter and you're done. Your program counter is the beginning of the block because you just jumped to the next block and you have to begin with the execution with the first instruction, zeroth instruction. And if it is returning the value, then just interpret the value and then return it. And if your block access is unreachable, then something went wrong, so you just report it. Oh, very strange things happen, so I'm just stop interpreting this program. So far, we discussed how to interpret a function from the very high level structure to the instruction and block access level. So this is pretty much almost everything about the interpretation of an IR. But please be noted that both IR and IR interpreter will be updated to take into account other types, some more types that we will discuss in this course. So please watch the repository and see what's going on in the upstream repository.